So welcome to this lecture on VHDL in the course Digital System Design with PLDs and FPGAs. In the last lecture we have seen various packages and various operators and how to use them and so on, and then we have started with the delay modeling available, the constructs available in VHDL. We will complete that delay modeling today. Also we will see some examples, that we have discussed quite a lot of things, and we will try to integrate to some kind of data path, sequential circuit. This whatever we have learned we will apply, we will take simple examples, so that it's not that we are going to do big things, but the examples to illustrate what we have studied, so that the basics are clear. Then you can do big things. The complex things are nothing but many simple things integrated, put together. So there is nothing very serious about it. So we will see simple things which illustrate the basics in the class, so that we have limitation of the slides. Suppose if I show you a huge code with which runs into some kind of 10 slides, you will not be able to keep track of it. Maybe when it comes to some case study I will still show the whole kind of VHDL code for reasonably complex designs, but for the time being we will stick to simpler example which illustrates the concepts. Okay. So let us run through the previous day's lecture, that is the packages, then delay modeling, and then we will complete the delay modeling today and see the examples. So let us run through the slides. So we have looked at the packages, and this is the primary standard logic definitions were involved in defined in this particular package. So you have standard U logic, standard logic vector, which is an unconstrained array. Standard U logic take all these values. Standard logic is a resolved standard U logic, that it resolves the multiple drives. Standard logic vector, standard U logic vectors are unconstrained array, and what extra defined in this mainly are the logical operators in standard logic 1164. Doesn't contain any arithmetic or relational operators. So if you use only standard logic 1164 package, you will not be able to do much. You have to do very basic things, or you have to build everything of your own. But the moment you start using other packages, many other things will be available. So we have the next in line is a standard logic unsigned package that uses standard logic and standard logic vector. You have all arithmetic operators, relational operators, shift right, shift left, and a function to convert to integer. Okay. So because what extra defined other than the standard library is only the standard logic and standard logic vector. So what required normally is a conversion function from standard logic vector to integer. That is what this does. You can convert, given a standard logic vector, you can give this as argument to this function, and it will return the integer, which is very useful, as I mentioned, maybe to refer to some indexes of memory array and things like that. Next the package which is not IEEE kind of defined package, which is a synopsis package within IEEE library. Now instead of standard logic vector, it uses array of standard logic as unsigned and signed, and you have so signed would mean it supports 2's complement for negative numbers, and you have arithmetic operators, relational operators. You have exactly like standard logic unsigned, as in the previous case you have SHR and SHL here, but this works as far as shift is concerned. If it is unsigned data type, then it will be a logical shift. If it is signed, then it is an arithmetic shift. So it takes care of the basically the sign extension. So if you have a 2's complement number, if you write shift, the sign number is shifted along, I mean the sign bit is shifted along, so that the value is correct for that width, that is a basic idea in signed arithmetic, otherwise basically it is something to do with the right shift, not the left shift. Okay. Then the next package is no, there is the conversion function in the standard logic arith package is this one: convert integer, convert unsigned, convert signed, or convert to standard logic vector. So these converts, like if you take underscore integer, it converts to integer all other 3. Similarly, if you take convert standard logic vector, then it converts all the other 3 to this and things like that. And the usage is this has to be in this order: standard logic 1164, standard logic arith, and standard logic unsigned. So there are some recommendations. You use basically arith for numeric operation, that is why it is put at the top of the unsigned, and for counters and test bench you do not use this arith, you just use the unsigned, and do not use the package standard logic signed at all. So you have an alternative IEEE numeric standard, instead of using a standard logic unsigned and standard logic arith, you can use this. That also contains a similar definition: unsigned and signed are the arrays of standard logic. Then you have arithmetic, relational, logical operators. You have shift left, shift right, rotate left, rotate right, and you have the conversion function, and this is the usage. You have the standard logic 1164 package, then you specify the numeric standard. And when it comes to the type conversion, between the base type and the subtype, it is you do not have to do anything, but if it is between say standard logic vector and integer, you use functions in the appropriate package like to integer, convert integer, and so on. But thing to remember is that suppose you want to kind of do type conversion between signed and standard logic vector, or unsigned and standard logic vector, both being defined as arrays of the standard logic, you can do a type casting as in C. That means suppose you have an unsigned vector, you want to convert it into a standard logic vector, you just say standard logic vector open bracket and you write the unsigned vector and the close bracket, then it is converted to standard logic vector. Similarly about the others, and if you have a numerical value, you can cast it to any of them by giving it using this kind of syntax. So that is about type conversion. Now mind you, the type conversion is a requirement of the VHDL basically to guarantee that the interface is proper. Like you have an 8-bit data bus, it is connected to only an 8-bit data bus, not like you define something in integer, something in standard logic vector, then if you connect it together and one is 8-bit and another is 16-bit, there is an issue. Similarly there is an issue with the most significant bit and least significant bit. All that is kind of guaranteed by this, and the code we write for conversion should not be synthesized. So that is indicated in the library that synthesis should be off during that conversion. And but I said when you convert and index, many a times it can imply a decoder kind of thing. So that is more to do with synthesis, but then it is better to understand these things so that you have clarity with which you can solve a lot of problem, at least you do not get a false alarm. And this is how the arithmetic is done. Normally if you have ABS as 8-bit, say S7 is a 7-bit number, S9 is a 9-bit number. So when you do simple addition like A plus B, the result is also 8 bit, you do not get a carry. Suppose you want a 9 bit along with the carry, which is a requirement when you do any kind of say shift and add in multiplication, you need the carry bit, carry out. So in that case what you do is that you append, convert this A and B to 9 bit, and the only way to do is that to append 0 at the MSB. So 0 and A plus 0 and B, then these are 9 bit, and you know that automatically the carry will come in the most significant bit, and that is assigned to S9. Suppose you want only, you have an two 8 bit numbers, you want only 7 bit result, then you can take the 7 bit of A and 7 bit of B, add it together. So A6 down to 0 plus B6 down to 0 is assigned to S7, and some case you want a carry input which is required, say you are forming a 2's complement number, so you have to invert it, invert some number and add 1 to it, then to get a 2's complement number for kind of signed arithmetic, then that can be achieved like this. You have A and B are 8 bit and result is 9 bit, and what we do is that we append the least significant bit of A with 1, and then C in is the least significant bit of B. Then this being 1, if the carry in is 0, no issue, nothing will be propagated to the next one. But if carry in is 1, the result at the least significant bit is 0, but there is a carry into the next place. So we have to ignore that last bit because that was added to get the carry into the chain. So we ultimately cast or assign S9 8 down to 1 to the result, ignoring the 0th part, because 0th part is just we have kind of manipulated to get the carry into the number. Okay, that is how the arithmetic is used. And when you want to do arithmetic with time, because the time is a physical unit which uses integers. Okay, so if you want a period to be multiplied for whatever reason, then what you do is that you take the time data, divide by 1 nanosecond, then you get the number without unit, cast it to real, then you get the period. Then you can recast it back to the time at the end of it, or many times this number is enough to keep on the computation. So that shows how to convert a time to real number to do some computation. Then this was what we started last lecture. We have in VHDL two types of delay, inertial and transport delay. Inertial delay is what a delay through the capacitive network. So if you have on a bus a capacitor and you apply a pulse, it takes some time to build up, and so there is a delay. Okay, or if you have a gate with a threshold value, you apply a pulse for the input to charge above the threshold, it takes a time and also propagate through the device. So unless the input value exceed that threshold, the output won't come. So there is a minimum pulse width which is required for this any gate to respond. Okay, so this inertial delay captures that minimum pulse width, also the propagation delay, both should be there. And the syntax is, suppose we say X gets A after 5 nanosecond, it means that if A will appear at the X with the delay of 5 nanosecond, but here it is assumed that you require a minimum pulse width of 5 nanosecond for the output to come. So anything below 5 nanosecond it makes no it does not appear at the output. Okay, so the another way of writing that is X gets inertial A after 5 nanosecond, inertial being the default, even if you do not say it's same as inertial. But if here the assumption is that the propagation delay and the pulse width are same, but if you have a different pulse width and At the gate level, as I said, it is difficult to model that. You have to look at the transistor level implementation, do the SPICE simulation and get those parameters. But if you know that parameters, this is an accurate depiction of the reality. Okay. So Y gets reject 3 nanosecond inertial A after 5 nanosecond, which say that anything less than 3 nanosecond should be rejected, output does not come. But if it is greater than 3 nanosecond, greater than or equal to 3 nanosecond, A will appear at the Y after a delay of 5 nanosecond. And we also said that you could write a continuous assignment like this. U gets 1 after 5 nanosecond, 0 after 8 nanosecond, 1 after 12 nanosecond. It means that from 0 to 5 it is 1, 5 to 8 it is 0, 8 to 12 it is 1. So you have a pulse width of 5 nanosecond at the beginning, then 0 width of 3 nanosecond, again 1 bit high for 4 nanosecond. So this is very useful in creating waveforms when you do delay modeling. Especially it is useful in applying some input waveform in the test bench, because in a test bench we give input to the various input of the entity and check the output. Okay. So this is quite a useful syntax. And transport delay is a delay which is model the delay through transmission line. So suppose you have a long transmission line, even if you give a narrow pulse, it travels all the way to the end, but it does not reject any pulse width. So that is done through this model, this syntax, which say Z gets transport A after 5 nanosecond. Okay. So which just Z is an exact replica of A with a delay of 5 nanosecond. That is the meaning of it. That is what we want in a transmission line case. And more than, do not think that we are going to probably model the transmission line. Yes, it can be like in an IC you have a wire delay, and the wire delay can be kind of model this. But there are some kind of sometimes some limitation with this when you do the timing model with this syntax. So the transport can be used in such places. So let us see an example, the behavior, the behavior of this inertial delay and transport delay. So this is a code I have written for simulating that, and you can write this code in any tool and try to simulate, you will get the result. I have not done a demo of a tool, but we will do it in the coming lectures. And first thing to note is that we are only doing a simulation and not a synthesis, because it is just purely simulation. This cannot be synthesized because this talks about time delays and all that. So there is no entity. So entity is empty. We are not defining any port. We could define only signals. We can define signal, that is good enough. Okay. So entity is kept, we give some name, it is kept empty. The architecture we give some name and of this entity is, and before the begin we declare all the signals we are going to use. So we have an A signal to which we assign some values and make a waveform, and to X, Y, Z we apply this syntax of inertial delay and the transport delay. So here you look, A gets 1 after 5 nanosecond, 0 after 11 nanosecond, 1 after 18 nanosecond and 0 after 22 nanosecond and so on. So to start with, you get 5 nanosecond 1 pulse, 6 nanosecond 0 pulse, 7 nanosecond 1 pulse and so on. Okay. And when it comes here, you see here the 28 to 30 is a small 2 nanosecond small pulse, then 30 to 32 is also only a 2 nanosecond pulse and so on. Okay. Now X is, we have written A after 5 nanosecond, it means that X is a delayed version of A by 5 nanosecond, but it rejects all the pulses below 5 nanosecond. When it comes to Y, it is again like X, it is a delayed version of A by 5 nanosecond, but anything less than 3 is rejected, not 5 now, okay. And Z is transport A after 5 nanosecond, and that is a delayed version of A by 5 nanosecond, no rejection. So if you simulate this, you will get a waveform something like this. So this is the original waveform we have created. So 5, 6, 7, 4, 6, then 2, 2, 6, 2, and it remains, okay. Now if you look at the A is a delayed version of 5 nanosecond. So we have 5, 10, 15, time is shown here. So X is delayed by 5 nanosecond, but you see, because minimum pulse width requirement is 5 nanosecond, everything below 5 is rejected. This 4 goes, this 2 goes, and this 2 goes, and you get like this 6 pulse width and this 6 combined, because this goes, it gets merged with that and you get that, okay. And the next one rejects below 3 nanosecond. So you can see it is exactly like X, Y is exactly like X, but now the 4 appears. Earlier the 4 was rejected because of this 5 nanosecond. So the 4 appears, and the last one is a transport delay. So Z is an exact replica of A with a delay of 5 nanosecond. So that is how the various delay models, and when it comes to simulation, I will show some kind of peculiarities, what happens because of certain syntax. Sometime it may give, if you use this for simulating some what to say, not so real life effect, you should understand that. We will see that when it comes to the some demonstration with the tool. Next thing we are going to try is that we write a kind of timing check, a VHDL code to check the timing of a flip flop, okay. Once again, this is used only while simulation, it cannot be used for synthesis. So you know that in a flip flop you have a clock coming, and the data, for proper transmission of data to the output, data has to arrive at the input some time called setup time TS before the clock edge, and also it should remain there, the data should remain there some time after the clock edge. It should be stable during this window, and this time after the clock edge is called hold time. That means you hold the value at the input, and the time before the clock edge is called setup time. That means you set up the data before some time. Now we want to write, and if that happens, the Q appears at the output with a delay of TCO, okay. Now in our code we are going to incorporate to check this timing violation. That means we have to check when the clock comes the setup time was correct or not. That means the data was set up some time before, whatever the setup time before the clock, and when the data changes we want to make sure that that data is changed after the hold time, okay. So the trick is basically we will, whenever there is an event like a positive edge on the clock, not the negative edge, what we will do is that we will check the difference between this time and the last event on D. If that is greater than setup time, no issue, otherwise you just flag a message saying that the setup time is violated. Similarly, whenever there is a data change, and of course we will update that time as the clock time, clock last event on the clock, and whenever there is an event on the data we will check that that time minus the previous event on the clock time is greater than the hold time. If it is violated, we print a message saying that it is violated, and we also update this time as the last event on the clock, because whenever there is an event on the clock we have to make sure that the difference between that and the last event on the data has to be greater than setup time. So we will keep two variables, one is to keep the last event on D, one is to keep the last event on the clock. Anytime an event happens we subtract the last event on the opposite, check greater than that time, that is the game. Okay, so we will look at the code. So this is a code which can be used in principle for simulating the behavior as well as for time check. So the library package clause entity is D and clock are input, Q is output. Now in the architecture declaration region we need to specify this setup and hold time. So we are specifying for EC, instead of hard coding it we could have said that this time minus that time is greater than 3 nanosecond, but to make it easily modifiable, easily configurable, we are defining a constant. So constant setup time some name is type time equal to 3 nanoseconds. So we have kind of defined that constant as 3 nanosecond. Constant hold time is type time equal to 1 nanosecond. So then we begin, and now you know that we write a process wherein we write the behavioral code for D flip flop, and we also check what happens if there is an event on D and if there is a positive edge on the clock. Now if you write only the behavioral code you need only the clock in the sensitivity list. Since we are checking the event on D we are including the D in the sensitivity list, otherwise you will not be like this process will not be computed whenever there is an event on the D. So we define two variables D L event and clock L event of the type time to kind of remember the time the simulation time whenever there was an event on the D and event on the clock. And then begin, this is the process begin, earlier was architecture begin, and now we write the behavioral code for flip flop. If clock tick event and clock is equal to 1 then Q gets D after 10 nanosecond, end if. As I said, when you write any code please include reset to make the code short, because I have less screen space I am avoiding it. So that is the behavioral code, and we are not like in this code we are not checking that whether there is any violation or at the input. Actually if the input is violated then we can't say Q gets D after 10 nanosecond, but our interest is in doing that checking the setup and hold time violation than reflecting that at the output. Okay. Anyway the message will be printed, so we know that the output is not going to come. So let us check the hold time violation. So that is a if D tick event then, okay, now we are using a new syntax which say assert. For a moment you forget about this, now assert now is the simulation time, the current simulation time. Okay. Now means the current simulation time minus clock last event. So that means that we are here, there is an event on the D and we have subtracted, or here it does not matter anywhere, we subtracted the last event on the clock which was stored, and we have to check it is greater than hold time. That is what it does. Now minus clock last event is greater than or equal to hold time. So the syntax of assert is like this, you say assert some condition which is we are expecting it to be true, we want it to be true. So and report some message severity some level. So the game is that if the condition is met it keeps quiet, okay, it does not do anything, but if the condition is violated it will report that message on the screen, and depending on the severity, say if it is, there are 4 levels of severity. It's called note, warning, error and failure. If it is note and warning, it will just print a message. If it is error and failure, it stops the simulation. Okay. So that is what we are going to use here, which say assert is now minus clock last event greater than hold time. That means if it is true, if there is no violation, don't do anything. If there is a violation, report hold time violation. Severity note, that means it will just print on the screen, on the console of the simulator, and we have to now update this variable. So D last event is now. Okay, that is what we do. Similarly, we check for the positive clock edge. Whenever clock tick event and clock is equal to 1, assert now, that is the event on the clock, minus D last event. So we are here. So if there is an event on the clock minus the last event on the D is greater than or equal to setup time. So just if it is violated, then report setup time violation, severity note. Then we have to update this this variable. So clock last event is updated with the current time, end if end process end time check. So it is done. So if you give this code and if you give simulate assigning some clock to the clock input, assign some input to D, then if it is violated that will flag the violation, or if this is interconnected to some other logic or registers and together you simulate, then this again shows the timing violation. You can catch the timing violation by message than on the, otherwise you have to go through the waveform and something is wrong, then you have to catch it. So this is one way of doing it, one useful way of doing it. So it illustrates this delay modeling or timing violation check, just an example. So I think that is where we kind of a brief look at the delay modeling. As I said, there are 2 delay models. One is inertial delay, which is used for the gates, which has 2 parameters: minimum pulse width for the output to come, a propagation delay. In the simplest case, the propagation delay and the minimum pulse width is assumed to be same, which is somewhat kind of near the kind of real life, but it need not be kind of exactly same, and you can specify a different pulse width. Then you have a transport delay, which kind of model the wires or the transmission line, the delay through that, because it does not reject, it appears at the other end of the transmission line. And we have seen a waveform to kind of study this effect by writing a code. Then we have seen a timing violation check on the setup and hold time of a flip flop. We have learned a new syntax called assert. So that is what we have done. As I said, as we go along and we do a tool demo, then I will illustrate some kind of peculiarities of this constructs. So let us now, since I think I would like to soon go back to the digital design to complete a little more there, then we can probably come to this VHDL back again for a short stint, and then we can go to the PLDs and so on. So let us take some example. So we have seen the example code for a demultiplexer. So I am not even showing the entity definition, but if you remember, if you refer to the last lecture, this is a 1 to 4 demultiplexer. So here the Y is the input, which is 4 bit, A, B, C, D are the output. That means it is a 1 which is demultiplexed to 4 output. Okay, Y is input, ABCD are the output, S is the select line. So since there are 4 outputs 1 to 4 the select line is 2 bit. Okay. So we have seen this code. The code is that since select line and Y are the inputs, we write in the sensitivity list and process SY begin, and the ideal, the best syntax for it is case, because there is no priority, and it for all the select line values we get the various outputs. So that is what case S is. When 0 0 A gets Y, all others get 0. 0 1 B gets Y, all others get 0. When 1 0 C gets Y and others get 0. When 1 1 D gets Y, all others get 0, and when others everything gets 0. But this is more of a kind of completion of the syntax that but not matters to kind of the synthesis. So that is a code. Now let us look at all possible ways of writing it. Even we will write if using an if, though the case is the ideal syntax, just to get a practice. So let us look at it. The first, let us write the simplest level, the Boolean equation. So you know that select line 1 is 0, select line 0 is 0, because you have S1 and S0 in select line, then A gets Y. So the equation is A of I, because there are 4 bits, A0, A1, A2, A3, or A3, A2, A1, A0, Y3, Y2, Y1, Y0. A of 0 is nothing but Y of 0 and S1 bar and S0 bar. Okay. Similarly for other things, when it comes to B of 0, it is Y of 0 and S1 bar and S0, so on. Okay. So we write the equation. So this shows the library, the entity where Y is input, which is 4 bit vector 3 down to 0, S is select line which is 2 bit vector, ABCD are the output which are all 4 bits. So it is a 1 to 4 demultiplexer with 2 selects line. Architecture begin, and symbol we write A0 is nothing but Y of 0 and not of S1 and not of S0. Similarly A1, A2, A3, B of 0 is Y of 0 and not of S1 and S0. All others are similar except for these index changes. C of 0 is nothing but Y of 0 and S1 and not of S0, because this is a 1 0, and when it comes to D of 0 it is Y0 and S1 and S0. Okay. Now this clearly shows, if you write you can write equations, but there is no point in repeating that. This index is very neat, A0 Y0, A1 Y1, A2 Y2, A3 Y3, and this remains the same. So we can write a generate loop for this and the next one. Okay. So that is what in the architecture. Now onwards I am not going to write the entity and library and all that. So you could write a generate loop which is say a label GLP for I in 0 to 3 generate and N generate. In that we say A of I is Y of I and not of S1 and not of S0. B of I is Yi and not of S1 and S0. C of I is Yi and S1 and not of S0. D of I is Y of I and S1 and S of 0. So this is simple enough. I mean you can write an equation, and if you are comfortable with it, though there is nothing wrong with the earlier one, you know that is nothing but a truth table, and we have seen how the equation of the case is, and that is exactly similar to this. So there is absolutely no difference between this equation and the case statement. So that is another way of writing, just mainly kind of playing with the syntax so that you are thorough. And so let us try with the concurrent statement the same thing. Now you know that when we use concurrent statement like with select and when else, unlike case and if, you can only specify one output. Okay. You can say A, but you cannot say say A and B together. Okay. So the one main problem with the concurrent statement is that you have to write a code for A, another code for B, another assignment for C and D. Okay. So let us use the with select. So here we say with S select A gets Y when 0 0, that means when S is 0 0. In all other cases it is 0, A is 0 when others. Okay. So that is the code for A. Similarly for B you have to write with S select B gets Y when 0 1, 0 0 when others. With S select C gets Y when 1 0, 0 0 0 when others, and with S select D gets Y when 1 1, 0 0 when others. There is absolutely nothing wrong with this coding because you know that though we say 1 to 4 demarks, if you look inside the circuit for A, circuit for B, circuit for C, circuit for D can be separated. Only thing is that A, B, C, D all are the functions, Boolean functions of Y and S. Okay. So it is natural, like you know that A, B, C, D all are the functions of the same A, B, C, D. It is very natural, it is very good that if you put it together in a case statement or if statement, it is very easy to understand than write it separately. Okay. It depends on synthesis tool. As far as the circuit is concerned, there is no issue that it should you should get the same effect, but definitely there is an issue that synthesis tool should understand that this together is a function. Okay. So maybe a naive very simplistic kind of synthesis tool will give you the correct result, correct circuit, but it may not infer that it is a 1 to 4 mux. That could pose some problem when you it will be good if synthesis tool knows that it is a 1 to 4 mux, because when ultimately you try to implement that in an FPGA using primitives, you can map it to the correct primitive. If you do not know that it is a kind of multiplexer or demultiplexer to place it to the correct primitive, to map it to the correct primitive, it could be a problem, but otherwise there is no issue with it. I haven't kind of looked at it whether synthesis tool infer that it is a mux. I am sure it most synthesis tool will do that, but you can check it. Like let us see the when else. Exactly like with select, you have to write the 4 concurrent statement for when else. So it's a gets Y when S is 0 0, else 0. Okay. B gets Y when S is 0 1, else 0. Similarly C and D, exactly same effect, though A, B, C, D, Y are functions of same Y, same as, we write it separate, but that is one kind of issue with this kind of coding. So I would suggest that you stick with in my opinion this is the best code. Of course we can have a concise version, we will see that, and you could use, this is the concise version. So we initialize A, B, C, D to all 0 at the beginning, and you say case S is when 0 0 A gets Y, rest all is 0 here, since whenever there is an event on S or Y the process goes from top to bottom. Say here A was assigned to 0 at the beginning for say the event happens at 100 nanosecond, A was assigned at 100 plus delta, but when it comes here A is reassigned with Y, so that is replaced with the Y, so there is no issue. This is a very nice code, when 0 0 A gets Y, when 0 get 1 B gets Y, when 1 0 C and so on, and here you can, instead of when 1 1 you get say D gets Y, I have said when others it's null, but you could combine others along with this. It is better to be precise with coding than take liberty. So in my opinion you can write others here, that's a better coding than writing like this. So this is perfect, but then you can write if also because instead of case if you write if, though it kind of has a kind of priority but since these are mutually exclusive and if you specify all the condition in if, it will kind of it is redundant, like you say when 0 0, like you say if 0 0 else if 0 1, but else if 0 1 is not of 0 0, but not of 0 0 will kind of when you make the truth table and kind of optimize it, everything comes back to the same thing. So you could write with an if, there is no issue there because the priority will be thrown out because all the conditions are specified, it will default to the same as old. So in principle you can write in the process sy instead of case you can write if. So you say if s is 0 0 then a gets y, all others get 0, else if s gets 0 1 then b gets y, everything gets 0, else if s is 1 0 then c gets y, everything gets 0, else d gets y, and see this else will capture everything else and there should not be an issue. And similarly you can have, instead of repeating all the other signals here, you could write initialize everything at the beginning and only what is changing could be written like in the case. And so these are kind of different ways of coding, but you know that like you can use if but the case is better, you can use with select and when else, but definitely the case or if is better, in that the case is better. In that there are two ways of writing it, one is very concise, less error prone, easy to understand. So I think you should be essentially using that. So sometime when you are faced with, I think it's important that you stick to the correct coding. So let us take another example, let us come back to the coding, let us take an example of an adder. We will look at a ripple adder, the code for a ripple adder. We will also look at the code for a carry lookup adder and how to write the adder. Though we may not use a carry lookup adder anywhere in our design, it is not required because it's huge, it's exponentially complex in terms of the product terms used. So we don't use it, but then it's a good example, good practice for writing the code. So let us go to the slide. So let us look at this. This is the ripple adder. Say I am considering, I am showing the picture of a 4-bit, but we are trying to implement an 8-bit adder. So I am only showing the 4-bit. You know that this is a full adder, you have A0, B0, C0 as the input, you have sum as the output and the carry as the output to the next stage, and here A1 B1 comes, sum 1 is the output, carry 2 is the output to the next stage. Now that is the equation, sum 0 is A0 XOR B0 XOR carry 0, carry 1 is A0 B0 or A0 or B0 and carry 0. Okay. So basically the carry 1 is generated if both are 1 1, then definitely there is 1 1, 1 plus 1 is 0, there is a carry, or if either of them is 1 then it is 0 1 is sum is 1, a carry input 1 will make it 0 and generate a carry, that is a game. So this is many a times is called generate, A B is generate, A or B is propagate. Okay. If A and B are 1 it generates a carry from this stage, if A and B are kind of either of them is 1 then it propagates the previous carry to the next stage, and that is how the rippling happens. Suppose this input is 1 and this is in propagate mode, this is in propagate mode, this is in propagate mode, that means you understand what it means, it is all 1 0 1 0 1 0. Then there is a rippling, there is a delay through this AND OR circuit, then that goes delay through the 2-level AND OR circuit, delay through the 2-level AND OR circuit. So you get, by the time the carry input comes here, C3 comes here, there is 6 levels of logic and it delays everything. This sum is delayed because this sum is going to use C3. So when it comes to the 4th one, it is much worse. Okay. So that's a ripple adder. So let us look at the code first, then we will go with the carry lookahead adder. So here there is library and we are going to write a neat code. So we have a carry in and we have a carry out. So we are going to have A0 to A7, B0 to B7, sum 0 to sum 7, a carry in and a carry out. Okay. So that is it. Port AB is 8 bit, sum is also 8 bit, but we have a C in which is a carry in standard logic, C out standard logic. Okay. Now when you write the equation, it has to be elegant. Now if you start, we are going to write a loop, generate loop, to say if you keep this as C in, there is an issue, because then that C in part has to be outside the loop, because that will not work, because then A0 B0 should be kind of combined with the C in. So it will be good if you declare an internal signal carry, because this is an internal signal, and we say carry 0 is C in. Okay. Similarly we have a carry 8, ultimately we assign it to the C out. So that is what we have done. Signal is carry, which is standard logic vector 8 down to 0 now. So because we have C0, C1, C2 all the way up to C8, which is a 9 bit vector, that is it. And we say carry 0 is nothing but the C in. C in we are assigning it to carry 0. It essentially like changing the name, there is no, as such there is no, this assignment does not mean anything, it is just we are changing the name. Similarly the carry 8 we are assigning it to C out. Now we can write a neat loop for GLP label for I in 0 to 7 generate. We say sum of I is A of I XOR B of I XOR carry I. Carry I plus 1 is AI BI, or that is generate, or AI or BI propagate, and CI. So it becomes very neat. If we had not made this assignment, not defined the carry like this, we would not be able to write everything in a loop, something has to be outside. So every time you write a code, make sure that you define the signals as assignments, so that things are very generic, kind of concise, elegant, and things like that. So now let us look at the carry lookahead adder. So in the carry lookahead adder, the game is that what we are trying to do is that in the ripple adder, when it comes to the carry 2, first the carry 0 is generated with A0 B0, and sorry, carry 1 is generated with A0 B0 C0, and that is used in this A1 B1 to generate C2. Now what we do is that we kind of, when it comes to C2, instead of rippling through, what we do is that we expand this C1. What is the equation? The equation say that carry 2 is A1 B1, or A1 or B1 and carry 1. So if you just expand it in terms of the carry 0 and flatten it, you will, when it comes to carry 2, you will generate it straight away from B1 A1 B0 B1 A1 C1 B0 A0 Z0, so that it is a 2 level structure. So instead of kind of what to say, a kind of modular adder, this is an adder which is, see, this is it is also surprising, it should, many times people do not question, like any combination circuit, you design, from the specification you write a truth table and you try to implement it. But surprisingly, when it comes to the adder, we make a 1 bit unit then you use that modular unit to cascade and build a kind of a ripple adder, okay. But that is not what we have used in a basic combination circuit design. The essential thing we used to do was that make a truth table and work out the equation and try to implement. And frankly, if you have a 8-bit adder, you write an 8-bit truth table, yeah, it is quite complex. Then you make the equations out of it, you try to implement, you will get a carry lookup adder. So in at least if you are kind of doing it properly in any learning, the carry lookup adder should come first, and we should be saying that there is an issue with such a scheme because it is exponentially complex in terms of area, and then so we adopt such a ripple adder. It is not that the ripple adder comes first from the principle and the carry lookup adder comes second. Definitely the carry lookup adder comes first, and because of these particular issue we default to the ripple adder. That should be understood. So maybe we can quickly look at the carry lookup adder structure in the next lecture. Maybe we will look at it in detail and kind of look at the VHDL coding, which is quite straightforward, but then it's a good exercise to do. So let us quickly look at the carry lookup adder. So this is basically say the C1. So the equation is SFI is AI XOR BI XOR CI, no issue with it. I mean for each stage the sum is same, but the main issue is with the carry, which it when it is modular, when it cascaded it ripple through. So we are trying to kind of expand it and try to build. So as like C2 comes, we are building A0 B0 A1 B1. When C3 comes we are building it in terms of A0 B0 A1 B1 A2 B2 and so on, okay. So that is a game, maybe that we will see in detail in the next lecture. So the last part we have looked at the various coding and example. We have tried various syntax of demultiplexer. I mean we applied for the case of a demultiplexer various syntax, though there is an straightforward easy elegant solution. We have looked at the ripple adder code, reasonable code. Once again we will not be using any of these, but then as I said, it's a practice. We briefly looked at what is wrong with the ripple adder, though as I said the other way should have been a better thing to do. And so I wind up here. Please revise it and I wish you all the best and thank you.